Section 4.4, laws of logs, that is, laws of logarithmic functions. A few homework problems for you. Okay, so laws of logs, say them in words first and then in symbols. So logs split a product into a sum, split a quotient, aka a fraction, into a difference, and logs let you pull exponents down in front. Okay, so here are the symbols. So this log, any base a here. So if you're taking the log of a product, the log will split that product apart into a sum. The log of the first thing plus the log of the second thing. Here's the log splitting apart a fraction or quotient. It splits it apart into a difference. And this is the one that's a little hard to say in words, but this is the log bringing an exponent out in front. The c here pops out in front of the log. Right, for these laws to hold, the numbers or the expressions, these a and b's here, have to be greater than 0. And the simple reason for that is that the domain of the log function, something that we looked at last time, is values greater than 0. So this a and the b, this capital A and B that are appearing on the right-hand side, they've got to be greater than 0, otherwise they're not defined. Okay, so we're going to use these laws of logs to do two things, expanding and maybe combining. It should be contracting maybe, but we're going to expand things and we're going to combine things. Okay, so expand means we're going to, write into more than one piece. We have a single log here, and we're going to apply the first log law here. So I'm just going to split this product 4x into a sum of two things, log base 2 of x. All right, so again, there's this condition here that's sometimes easy to forget, and it can catch you flat-footed sometimes. This is valid only for x's being greater than 0. I guess we could also simplify this. We might as well. Log base 2 of 4. Let's see. Let's go ahead and do that as an example of cancellation here. Remember, 4 is 2 to the 2. And so log base 2 of 2 to the, those are canceling, and this comes out to be 2 plus log base 2 of x. Okay. Another example, quite a bit more complicated, this one. So the thing that we're taking the log of, this time it's the natural log, it has an exponent up top. And so we're going to apply the third rule, I guess, so that that exponent can come out in front. Right? And then what's left behind is, just the x over x plus 2. But we're going to try to expand fully. I guess the word, the catch is right there, is fully. So we're going to apply another log law to split this quotient apart. Right? We are going to need to keep track of the parentheses out in front here. This 1/2 is going to be multiplied by the entire expression here, natural log x, and then the quotient turns into a difference, x plus 2. And it's important not to get carried away here. There is no log law for splitting apart this sum of x plus 2. So that's as much as we can do. Okay, so I'm going to try to do these UGOs. So whenever you see a UGO, what I'm going to ask you to do is pause the video and give it a try. So we're still in the expand problem. So try to expand that out. And then I'll click on the solution and show it to you, but not give you a lot of commentary. So again, you push pause. I don't want to make the video longer than it needs to be. Here's the solution. Okay, hopefully you did press pause, try it out on your own, and then came back and had this as your solution. Again, I said I wasn't going to do a lot of commentary, but the first thing, we see this is a quotient. We split it apart into a difference. And then the additional thing that we can do is bring the exponent down in front here. Okay, so that's the one direction. We split a single log into many, hopefully simpler logs. And the other direction is starting with several logs and try to combine them up into a single log. Okay, so here we're on the right-hand side of the first rule. That is, we have a sum of two separate logs. running the rule in reverse says that's going to be the log of the product of the two numbers. Okay, so the instructions here say combine and evaluate. So if we're actually going to evaluate this, what we're going to need to do to evaluate by hand is to recognize this 9 times 24 as a power of 6. So for that reason, I'm going to write 9 as 3 squared, and 24, let's see, that's 3 times 8, and 8 is 2 cubed. Okay, so we've got 3 times 3 times 3 and 2 times 2 times 2, and hopefully I'm not making this more complicated than having just gone to the calculator, but 3 3s and 3 2s multiplied together to give us 6 3s. So this is going to be 3. If we had simply just multiplied these two numbers together, I don't know about you, but at least I would have been a little hard-pressed to know that, 216, that was 6 cubed. By factoring, we gave ourselves a better chance at doing that. Okay, so here we're going to, again, try to combine. Let's see. Let's maybe group them. How should we group them? Let's group the first, we'll deal with the first two and then the third one. So these first two, they're a difference, and so the second log rule will tell us that that's the log base 2 of 6 over 15. And then we're still dealing with this other log being added on. So this is the sum of two things. So the log law says that we can take the single log of the product, 620 over 15. The product is 6 over 15 and 20. Okay, so maybe should be doing this cancellation by hand, but I'll go ahead and let the computer knock that down to the number 8. 8 is 2 cubed, and so this evaluation turns out to be 3. Okay, so that's at least one example of why you might choose to combine logs here. We'll try to explain why we split logs apart, the thing that we did prior, but one reason to combine logs is we were able to successfully evaluate this expression after we combined them, but we wouldn't have been able to do that by hand before we combined them. We can't say what log base 2 of 6 is by hand, but we were able to say what log base 2 of 8 is. Okay. Right, so one more example. Again, this is the symbolic one. And what distinguishes this from the previous example is you have to see that there are coefficients or constants in front of your logs. And the key point in combining to a single log in a problem like this is to make sure you first move the coefficients up into the exponent spots. Right? We're using law 3 in reverse. Okay, so let's see if I can do that. So this is log base 10, and this is x raised to the 4th. Now, I strongly encourage you to use these parentheses when you write this expression. To me, writing log x to the 4th without parentheses is ambiguous. I'm not sure if the 4 goes just on the x or if it goes on the log of x. So that's why I like these parentheses. Right? So they're not bad in that first one. They do get just a little busy here because now I've got to have x minus 2. I need parentheses around it, and that's the thing that's being squared. But I need another set of parentheses for my log function. Right? And this third one, I could do either option here. I could either move a negative 3 up or the positive 3 up. I think I'll just move the positive 3 up, and so the minus sign will stay downstairs. The option was to make this a plus sign here and put a minus 3 in the exponent spot. Okay, that's the key step, key point. Let me put that in bold. Got to get the coefficients up to the exponent spots first, and now we can combine the remaining logs using rules 1 and 2. All right, so let's do them one at a time here. This log of, this will be x to the 4. So that this is the sum that we're looking at here. Well, let me box that. I'll make it look nice in the PDFs. And we take the product of the two terms there, and then we're still subtracting off this third. So we have the difference of two things at this point. Difference of two things, not two things, two logs. That's the key point here. And so the second law says we're going to turn this into the single log of the quotient. So this would be log, whoops, what did that happen? Oh, I missed one parenthesis. I guess I don't need that parenthesis here. So the log of this thing divided by this thing. Okay, so it does get a little bit complicated with these coefficients, but just remember to do that as the first step. Move the coefficients up to exponent spots, and then begin to draw things together into products and quotients. Let's see, it's going to be a pretty short lesson today compared to yesterday's, but I guess I can still timestamp here. This is at 11:25. Change of base formula. Okay, so the idea here is that we're going to try to express the log base A of x in terms of some other log base. And this is log base B. And this is set up to work for any A and B, but typically what happens here is that you're needing to compute, say, log base 7 of some number, and your calculator doesn't have a log base 7 button. So the idea is to convert your calculation over to log base 10 or log base E, the common or natural logs, so that you can use your calculator to do the evaluation. Well, here's the formula, and try to give you a memory aid for memorizing it, and I'll try to show you how you can recover the formula if you forget. But the general idea here is that you know that you have log A, and you're trying to replace it with log B, so the right-hand side should have the log B's on it, log base B and log base B. It is a quotient. And then the memory aid that I try to remember here is that the letter that's lower on the left side is the letter that's lower on the right side. The X is the one that goes upstairs. Okay, so yeah, so log base 2, maybe your calculator's got a log base 2 button, but if not, this is how you could change to log base 10. So log base 10, remember, this is a common log, we don't need the subscript here. So log of, and on the left-hand side, 14 is the higher number, so on the right-hand side, 14 is the higher number. Okay, so that's the conversion. Doesn't ask for a decimal here. All right, so maybe this could wait to the tutorial, but I guess I'll go ahead and do it now. So if you want to convert log base 2 of 14 to log base 10, what we just did, but you're blanking on the formula, here's a possible way that you might be able to do this problem. Right? So you're going to work with this equation. You're going to set y equal this thing that you need. Right? So this is an equation, and it's got log base 2 in it. You want to get rid of the log base 2. You're converting from log base 2 to something else. So you want to ditch log base 2. How do you get rid of log base 2 in this equation? Well, what's going to kill off log base 2 is if we exponentiate both sides. So 2 to the log base 2. That's the cancellation taking place there. So the right-hand side now, the cancellation 2 to the log 2 is going to leave just the 14. Okay, the idea was to switch to log base 10. So now what you're going to do is take this equation and introduce log base 10. And well, how are we going to do that? We're just going to take log base 10 of both sides. And again, log base 10, we don't need the subscript. Okay. Don't lose track of what we're doing here. We're trying to find the y. So we've got to solve this equation for the y. And right now this is looking hard because this log base 10 and 2 to the, they don't cancel. But the key idea here is that we're, instead of using the cancellation to get this this variable downstairs, what we're going to do is use the third law of logs. It says that exponent y can come out front. Okay, and then the last step here is to remember what we're doing. All along we've been trying to compute what y is, and so the last step is simply to solve for y. And of course we get the same answer as we did last time. Log base 10 of 14 over log base 10 of 2. Okay, we're at 15 minutes. Yeah, I guess I'll put that in. 15:45. We just stated the log laws at the very start. Log of a times b is equal to log of a plus the log of b. I don't think I'm going to ask you to prove these laws, but just so they're not entirely mysterious, all these laws rely on are the cancellation laws for exponents and exponentials and logs, and then exponent laws that you already know or need to review. Okay, so we start with log of a times b, and this is the cancellation law. Like, okay, it seems crazy. Well, why are you doing this? I don't know, but a is equal to 10 to the log a. That's cancellation. And the b is equal to 10 to the log b. Okay, and now what we do is use the rule for exponents. So we have 10 to the something times 10 to the something else. The rule of exponents says we add these two exponents. Well, I don't know if I needed to do a copy paste there, but that's what I did. Okay, so this is rule of exponents. Maybe I'll put that in a note here. Rule of exponents. And then the last thing is now to apply cancellation again. We're taking log base 10 of 10 to the, and it comes out just as the to the. And that's the proof of that law. The others are similar. Okay, the last thing here is always troubling for me. I don't know if I do more harm than good when I tell you things that logs don't do. Maybe you never would have thought that they did this, but these are errors that I see fairly often and things that you have to try to resist. Try to make sure that you don't make this mistake. The logs do not break apart sums, nor do they break apart a difference. So I talked about this briefly here. This exponent that comes out in front, it has to be inside of the log function, right? If we see an expression like this, where the parentheses are around the entire log function, this exponent does not come out in front. Right, and then logs don't cancel. I've seen this, students try this before. It seems on the face like, oh, this looks possibly reasonable, but it doesn't work. We can't cancel the 10 and 2 down to 5. Even worse, I've seen sometimes students actually try to cancel the word log from both expressions. Well, log divided by log, they cancel, but that doesn't work either. There are actually a long list of problems or questions like this in one of your homework problems asking you about true or false, are these log laws true? And we might go over those tomorrow.